Hello friends, in our previous discussion on combinational logic circuits, we talked about the parallel binary adders, the ripple carry and the look ahead carry adders, their IC datasheet characteristics and application. In today's lecture, we shall look at the basic function of a comparator, use of the exclusive OR gate as a basic comparator, then analyze the internal logic of a magnitude comparator that has both equality and inequality, and then we will talk about the decoder. A decoder is a digital circuit that detects the presence of a specified combination of bits on its inputs and indicates the presence of that code by a specified output level. Comparators. The basic function of a comparator is to compare the magnitudes of two binary quantities to determine the relationship of those quantities. In its simplest form, a comparator circuit determines whether two numbers are equal. As you learned in earlier discussions, the exclusive OR gate can be used as a basic comparator because its output is a 1 if the two input bits are not equal and a 0 if the input bits are equal. Figure shows the exclusive OR gate as a 2-bit comparator. In order to compare binary numbers containing 2 bits each, an additional exclusive OR gate is necessary. The two least significant bits of the two numbers are compared by gate G1 and the two most significant bits are compared by gate G2 as shown in here. If the two numbers are equal, their corresponding bits are the same and the output of each exclusive OR gate is a 0. If the corresponding sets of bits are not equal, a 1 occurs on that exclusive OR gate output. In order to produce a single output indicating an equality or inequality of two numbers, two inverters and an AND gate as shown can be used. The output of each exclusive OR gate is inverted and applied to the AND gate input. When the two input bits for each exclusive OR are equal, the corresponding bits for the numbers are equal, producing a 1 on both inputs to the AND gate and thus a 1 on the output. When the two numbers are not equal, one or both sets of corresponding bits are unequal and a 0 appears on at least one input to the AND gate to produce a 0 on its output. Thus, the output of the AND gate indicates equality or inequality of the two numbers. The basic comparator can be expanded to any number of bits. The AND gate sets the condition that all corresponding bits of the two numbers must be equal if the two numbers themselves are equal. Inequality. As shown in the logic symbol, for a 4-bit comparator, in addition to the equality output, many IC comparators provide additional output that indicate which of the two binary numbers being compared is the larger. That is, there is an output that indicates when number A is greater than number B and an output that indicates when number A is less than number B. To determine an inequality of binary numbers A and B, we first examine the highest order bit in each number and we have the following conditions which are possible. First, if A3 is equal to 1 and B3 is equal to 0, number A is greater than number B. If A3 is equal to 0 and B3 is equal to 1, number A is less than number B. If A3 is equal to B3, then you must examine the next lower bit position for an inequality. These three operations are valid for each bit position in the numbers. The general procedure used in a comparator is to check for an inequality in a bit position, starting with the highest order bits. When such an inequality is found, the relationship of the two numbers is established, and any other inequalities in lower order bit positions must be ignored because it is possible for an opposite indication to occur. The highest order indication must take precedence. Decoders. A decoder is a digital circuit that detects the presence of a specified combination of bits on its inputs and indicates the presence of that code by a specified output level. In its general form, a decoder has n input lines to handle n bits and from 1 to 2 to the power n output lines to indicate the presence of one or more n bit combinations. Here we shall be discussing the basic principles of several decoders, and these basic principles can be extended to other types of decoders. The basic binary decoder. Suppose you need to determine when a binary 1001 occurs on the input of a digital circuit. In such a situation, an AND gate can be used as a basic decoding element because it produces a high output only when all of its inputs are high. Therefore, you must make sure that all the inputs to the AND gate are high when the binary number 1001 occurs, and this can be done by inverting the two middle bits as shown in the figure. The logic equation for the decoder of figure A is developed as illustrated in figure B. One should verify that the output is 0 except when A0 is equal to 1, A1 is equal to 0, A2 is equal to 0 and A3 is equal to 1 are applied to the inputs. A0 is the least significant bit and A3 is the most significant bit. If a NAND gate is used in place of an AND gate as shown in the figure, a low output will indicate the presence of the proper binary code, which is 1001 in this case. The 4-bit decoder. In order to decode all possible combinations of 4 bits, 16 decoding gates are required. This type of decoder is commonly called a 4-line to 16-line decoder because there are 4 inputs and 16 outputs, or it could be called a 1 of 16 decoder because for any given code on the input, one of the 16 outputs is activated. A list of the 16 binary codes and their corresponding decoding functions are given in the table. If an active low output is required for each decoded number, the entire decoder can be implemented with NAND gates and inverters. In order to decode each of the 16 binary codes, 16 NAND gates are required. AND gates can be used to produce active high outputs. A logic symbol for a 4-line to 16-line decoder with active low outputs is shown in figure. The bin/DEC labels indicate that a binary input makes the corresponding decimal output active. The input labels 8, 4, 2 and 1 represent the binary weights of the input bits. The 74HC154 1 of 16 decoder. The 74HC154 is a good example of an IC decoder. There is an enable function provided on this device, which is implemented with a NOR gate used as a negative AND. A low level on each chip, select input CS1 and CS2 is required in order to make the enable gate output high. The enable gate output is connected to an input of each NAND gate in the decoder, so it must be high for the NAND gates to be enabled. If the enable gate is not activated by a low on both inputs, then all 16 decoder outputs will be high regardless of the states of the 4 input variables, that is A0, A1, A2 and A3. Application of decoders. Decoders are used in many types of applications. One example is in computers for input/output selection as depicted in the journal diagram. Computers must communicate with a variety of external devices called peripherals by sending and or receiving data through what is known as input/output ports. These external devices include printers, modems, scanners, external disk drives, keyboard, video monitors and other computers. As indicated in figure, a decoder is used to select the input/output port as determined by the computer, so that the data can be sent or received from a specific external device. Each input/output port has a number called an address, which uniquely identifies it. When the computer wants to communicate with a particular device, it issues the appropriate address code for the input/output port to which that particular device is connected. The binary port address is decoded and the appropriate decoder output is activated to enable the input/output port. As shown, binary data are transferred within the computer on a data bus, which is a set of parallel lines. For example, an 8-bit bus consists of 8 parallel lines that can carry 1 byte of data at a time. The data bus goes to all of the input/output ports, but any data coming in or going out will pass only through the port that is enabled by the port address decoder. The BCD to decimal decoder. The BCD to decimal decoder converts each BCD code into one of 10 possible decimal digit indications. It is frequently referred as a 4-line to 10-line decoder or a 1 of 10 decoder. The method of implementation is the same as for the 1 of 16 decoder previously discussed, except that only 10 decoding gates are required because the BCD code represents only the 10 decimal digit, that is 0 through 9. A list of the 10 BCD codes and their corresponding decoding functions is given in the table. Each of these decoding functions is implemented with NAND gates to provide active low outputs. If an active high output is required, AND gates are used for decoding. The logic is identical to that of the first 10 decoding gates in the 1 of 16 decoder. the BCD to 7 segment decoder. As shown in the logic diagram, the BCD to 7 segment decoder accepts the BCD code on its input and provides output to drive 7 segment display device to produce a decimal readout. The 74LS47 is an example of an IC device that decodes a BCD input and derives a 7 segment display. In addition to its decoding and segment drive capability, the 74LS47 has several additional features as indicated by the LT, RBI, BI/RBO functions in the logic symbol. As indicated by the bubble on the logic symbol, all of the outputs, that is A through G, are active low, as are the LT or lamp test, RBI or ripple banking input, and BI/RBO or blanking input / ripple blanking output functions. The outputs can drive a common anode 7 segment display directly. In addition to decoding a BCD input and producing the appropriate 7 segment outputs, the 74LS47 has lamp test and zero suppression capability. When a low is applied to the LT input and the BI/RBO is high, all of the 7 segments in the display are turned on. Lamp test is used to verify that no segments are burnt out. Zero suppression is a feature used for multi-digit displays to blank out unnecessary zeros. For example, in a 6-digit display, the number 6.4 may be displayed as 006.400 if the zeros are not blanked out. Blanking the zeros at the front of the number is called leading zero suppression, and blanking the zeros at the back of the number is called trailing zero suppression. Keep in mind that only non-essential zeros are blanked. With zero suppression, the number 030.080 will be displayed as 30.08, that is, the essential zeros remain. Zero suppression in the 74LS47 is accomplished using the RBI and the BI/RBO functions. RBI is the ripple blanking input and RBO is the ripple blanking output on the 74LS47. These are used for zero suppression. BI is the blanking input that shares the same pin with RBO. In other words, the BI/RBO pin can be used as an input or an output. When used as a blanking input, all segment outputs are high or non-active. When BI is low, which overrides all other inputs. The BI function is not part of the zero suppression capability of the device. All of the segment outputs of the decoder are non-active or high if a zero code is on its BCD input and if its RBI is low. This causes the display to be blank and produces a low RBO. So friends, that brings us to the end of our discussion in this lecture, and therefore we sum up. In this lecture we learned that the basic function of a comparator is to compare the magnitudes of the two binary quantities to determine the relationship of those quantities. In the simplest form, a comparator circuit determines whether two numbers are equal. The exclusive OR gate can be used as a basic comparator because its output is a 1 if the two input bits are not equal and a 0 if the input bits are equal. Then we learned that a decoder is a digital circuit that detects the presence of a specified combination of bits on its input and indicates the presence of that code by a specified output level. In its general form, a decoder has n input lines to handle n bits. So, that is it for today. See you in the next lecture with more on logic circuits. Thank you very much.